Listen closely. That is not the sound of the future. That is the sound of the present tense. In the previous chapters, we explored the architecture of the mind. We built the digital cathedrals of the transformer model. We watched as the forge of backpropagation hammered random noise into coherent intelligence. We talked about math, abstraction, and software. But software cannot exist in a vacuum. Code is not ethereal. Every thought generated by ChatGPT, Gemini, Kimi, and other tools, every pixel generated by tools like Midjourney, Leonardo, every translation, every prediction, they all have a physical cost. Intelligence is expensive. It demands energy and generates heat. It requires a physical substrate capable of performing quintillions of mathematical operations per second without failure 24 hours a day. We used to think the bottleneck for AI was algorithms. We were wrong. The bottleneck was never just the math. The bottleneck was the physics of moving electrons through silicon. Today, the world is locked in a new kind of arms race. This race is not fought with missiles or armies, it is fought with nanometers. It is fought with lithography machines worth hundreds of millions of dollars. It is fought over access to the most complex objects humanity has ever created, the AI accelerators, the GPUs. This is AxiomTech, and I am Epoch. In this episode, we leave the abstract realm of software and descend into the brutal reality of hardware. We will tear apart the silicon engines powering this revolution. We will understand why a gaming component became the most valuable technology on Earth, and we will look at the terrifying engineering required to build the next generation of synthetic brains. Welcome to the Silicon Wars. To understand why the modern GPU is a great option for AI workloads, we first need to understand the central processing unit, the CPU. For 70 years, almost every computer on Earth, the smartphones in your pocket, even a supercomputer simulating nuclear weather, has been built on a single foundational idea, the von Neumann architecture. Proposed by physicist and mathematician John von Neumann in the 1940s, this architecture is brilliant in its simplicity and flexibility. You have a processing unit that does the math. You have a memory that holds both the data and the instructions on what to do with that data. And there is a data path connecting them. The CPU fetches an instruction from memory. It executes the codes and writes the result back to memory. After these operations, it moves to the next instruction and fetches that instruction. This approach is excellent for general-purpose computing. Running an operating system, browsing the web, compiling code, these are fundamentally serial tasks. They require complex logic, lots of branching, and unpredictable memory access patterns. The modern CPU, like an Intel Core i9 or AMD Ryzen 9, is an engineering marvel designed exactly for this purpose. It is optimized for low latency. It has massive on-chip caches to keep data close. It has incredibly complex branch prediction hardware to guess what code will run before it even happens. It runs at blindingly fast clock speeds, for example, 2.5 GHz, 3.8 GHz. But then, deep learning arrived. And deep learning doesn't care about complex branching logic. It doesn't need low latency for a single operation. Remember what we learned in the previous episodes. What is a neural network at its core? It is matrix multiplication. It is multiplying a giant grid of numbers by another giant grid of numbers, adding a bias, and passing it through a simple activation function, like ReLU. Training a model like GPT-4, Gemini, Kimi involves doing this not millions, but septillions of times. These operations are frighteningly simple. You don't need a Ferrari to move a mountain of dirt. You need a bulldozer. When you try to run modern deep learning on a traditional CPU, you hit two catastrophic walls. First, the compute wall. A CPU typically has 8 to maybe 64 complex cores. Even with vector instructions like AVX5112, it cannot perform enough simultaneous mathematical operations to process the data required for AI. It is too smart for its own good. Its complex control logic is wasted silicon when all you have to do is multiply A by B a trillion times. The second, and perhaps more deadly obstacle, is the memory wall. This is the curse of the von Neumann architecture in the age of big data. The CPU is fast, and unfortunately, the memory is slow. The bus connecting them is narrow. In AI workloads, The CPU spends most of its time doing absolutely nothing. It is waiting. It is waiting for weights to be fetched from DRAM. The processor is starving for data. We call this being memory bound. Even if you had a CPU running at 100 GHz, it wouldn't matter, because it cannot get the numbers fast enough to process them. By roughly 2010, it became clear to researchers like Jeff Hinton, Yann LeCun, and Bengio that their algorithms were being strangled by hardware designed in the 1950s. They had the mathematical blueprints for intelligence, but they did not have the engine to run it. Salvation did not come from the supercomputing labs of IBM or Cray. It came from teenagers playing Crisis. While AI researchers were hitting the CPU wall, another industry was facing a strangely similar mathematical problem: 3D gaming. Rendering a realistic 3D scene in real time, at 60 frames per second, is a brutal mathematical challenge. Every single pixel on your 4K screen must be calculated simultaneously. What color is it? Is it in shadow? Is it reflective? What is its coordinate in 3D space relative to the camera? To do this, you need to perform linear algebra on massive vectors and matrices of geometry data. Does that sound familiar? The math required to render a dragon in a video game is shockingly similar to the math required to train a neural network to recognize a dragon in a photo. It's all just massive, parallel matrix operations. To solve this gaming problem, a new type of processor was invented in the late 90s, the Graphics Processing Unit, the GPU. Companies like 3DFX, ATI, and a young, aggressive company named NVIDIA entered an arms race to build chips that were the exact opposite of the CPU. While the CPU was a few smart cores, the GPU was thousands of dumb cores. A GPU doesn't care about complex branching. It doesn't need massive caches because it's constantly streaming data, not jumping around randomly. It is designed for one thing: throughput. It is designed to take 1 million small mathematical tasks and execute them all at the exact same instant. This is called SIMD, single instruction, multiple data. You tell 10,000 cores to multiply by 2, and they all do it to 10,000 different numbers simultaneously. For a long time, these GPUs were fixed function devices. They were hardwired only to do graphics tasks. You couldn't just run Python code on them. But in roughly 2006, NVIDIA and its CEO, Jensen Huang, made a bet that would eventually make them the most important company on the planet. They realized that this massive parallel computing engine they had built for gamers could be used for anything that required parallel math. They created CUDA, Compute Unified Device Architecture. CUDA was the key that unlocked the GPU. It was a software layer and a programming model that allowed developers to write C++ code that ran directly on the GPU's thousands of cores, bypassing the graphics pipeline entirely. And in 2012, the inevitable happened. Alex Krzyzewski and his team used 2 NVIDIA GTX 580 gaming GPUs to train a convolutional neural network called AlexNet for the ImageNet competition. They crushed the competition. The error rate dropped almost by half overnight. The CPU era of AI was over instantly, and the GPU era had begun. NVIDIA had almost monopolized this new paradigm, having spent years cultivating the CUDA ecosystem. They cornered the market not just with hardware, but with software dependency. But as neural networks deepened from millions to billions to trillions, even the mighty gaming GPU began to buckle. The demand for compute was doubling not every 2 years as Moore's law predicted, but every 3.5 months. In our next video, we will examine the dedicated AI chips developed by NVIDIA. In a world of 80 billion transistors, massive bandwidths, and boundary-pushing digital design, we will tear down the world's most powerful chip, the NVIDIA H100. This is AxiomTech, and I am Epoch. See you in the reality of engineering.